Hello. All right. If I talk too softly or too slowly, let me know. That's a joke. I'm loud and fast. So if you read, for those of you who are students, if you read anything about giving talks, the very first thing they say is, never start out with an apology, right? Like, oh, I'm so sorry, but I must, because I've been incredibly busy and I never really put time into making this talk. So what I did is I took a little bit of talk that I did at a workshop last fall and a public talk I did and kind of blended them together like literally 20 minutes ago. So I'm sorry. So star bars. So I got interested in a few years ago in survey science. It's all the rage now in astronomy. So let's start off with a quick little review. So the very first all-sky survey was done in the 1950s. In Los Angeles, the Palomar All-Sky Survey. The telescope is right there. It was about a 1 meter telescope, slightly larger. And what it did is it took an image of every region of the sky that was visible from the location of the telescope. And I think it took about 7 years to do this. And the detectors at the time were 18-inch square glass plates, right? And it used two filters, which was limiting in the science. And the thing about photographic emulsion is that its response is nonlinear to light. So if you want to relate the optical density on the photographic film to how much energy landed on the focal plane, it's a complex thing to unravel, right? So someone had the idea, hey, in the 90s or whenever the idea was originally conceived, let's do it now with modern technology. So this is the telescope that performed the Sloan Digital Sky Survey. And this telescope is in New Mexico. It's twice as big as the Palomar All-Sky Survey telescope. It's about 2 meters, a bit more than 2 meters. And it took an image of a very large region of the sky known as the North Galactic Cap. It took about 5 years to do this. And the thing about each of these telescopes is that they looked at each region of the sky only once, right? So we just got a picture of that region of the sky. Sloan had a very small region of the sky known as Stripe 82 that it revisited. It imaged the same part of the sky about 30 times, okay? And Sloan was different from Palomar in that it had 5 photometric filters. So your scientific reach was, you could do more science, and also there was one more aspect that I forgot. Well, let's just move on. It had a digital detector, which has a linear response to light, right? So it's much easier to relate the energy at the focal plane to the energy that left the object. So now we're currently planning the Large Synoptic Survey Telescope. So you'll notice that in each image, you have a human, right? You have a human there, have a couple of humans here, and you have a superhuman. Because based on the size of the telescope, these people are about 12 feet tall. And so this is an 8.5 meter telescope aperture. And what it's going to do, whereas the Palomar telescope was about 1 meter, the Sloan Digital Sky Survey telescope was over 2 meters. This is 8.5 meters, whereas the Palomar All-Sky Survey took 7 years to image the entire sky once, and Sloan took about 5 years to image the sky. LSST is going to image the entire sky every 3 days in 6 photometric filters. So what we're going to end up with is a deep HD movie of the night sky. All right? And this survey is going to go on for 10 years. And when I say it's going to image the entire sky every 3 days, that's in a given filter, right? The actual entire sky is going to be covered every night. And so I've been, this is going to be a deluge of data. And so the way that astronomers have typically worked with data fundamentally must change, right? Typically, people actually look at images, right? And oh, there's an interesting thing there, right? And so you can't do that when you download 10 terabytes of data per night, as LSST is going to do. So I am going to talk to you a little bit about how important movies have been in science. So ahead of the astronomers, the solar physicists have been dealing with movie data for some time now. So here's our sun, unassuming ball of gas, right, that our planet orbits. But if you look at it closely, is it possible to change the lighting a bit? Because it's not. I have an incredibly soothing voice, so if the lights go dim, don't fall asleep. But if you look closely, you see that it's a very dynamic atmosphere, right? These are so-called spicules. The scale here, each tick mark is a megameter, a million meters, right? And the size of the Earth, what is the size of the Earth? It's on a scale of 10 to the 4 kilometers, so that would be like 10 to the 7. So, the Earth is like just bigger than one of these ticks here. If we look at the sun in X-rays, we see there's a very dynamic, energetic atmosphere. We have these very large regions we call active regions and bright points. And so it's only with movies that we've been able to begin to unravel a lot of the processes that heat the plasmas, right? The surface of the sun is roughly 6,000 degrees, and these plasma loops that we see here are millions of degrees. And so you have this 1,000 degree surface, 6,000 degree surface that indefinitely maintains this million degree atmosphere, right? And that's known as a coronal heating problem. And it's not well understood traditionally how this works, and we know that it's involved with either waves or magnetic reconnection processes. This is a flare that shows you magnetic reconnection. And here, if we look at the pole of the sun, we see these events known as jets. Gravity at the surface of the sun is about 30 times stronger than gravity at the surface of the Earth. And yet the Earth's atmosphere is not leaking out in interstellar, interplanetary space. So why is the sun's atmosphere doing that, right? How is this plasma acceleration taking place? And it's only through these movies that we can see this. And here's an image of an asteroid, right? So in terms of mapping out the solar system, what we can do is we can find objects, and based on their dynamics, recently people discovered what are known as collisional families, right? So these are families of objects on similar orbits, which mean that they had similar origins. And so by looking at many objects, we can unravel the details of how the solar system was assembled. And recently now, with the Kepler Space Telescope, the notion of planetary transits, planetary transits are routinely observed now. And so we have something like 800 confirmed exoplanets observed and over 2,000 candidates. And based on the details of these light curves, which is the brightness of the object versus time, one is able to figure out interesting physical information about the system. So here we see the interaction of the planet's atmosphere and the star, and you get this type of structure in between the primary and secondary transits. And here, for example, is a very rare type of object where you have a nice star, and then suddenly it does something unexpected. It disappears. My theory is that a dragon eats it and belches it back up. There are the so-called R-core borealis stars that, it's believed that they output a large ball of gas. I don't remember what exactly is going on with this object. I think it's a transit by another object. You want to come with the lights again? Yeah. So what am I doing? So survey science. Did you guys see my nice star guy? So we have this project. We call it star bars because we're using variable stars as tools. Okay. And what we want to do is we want to address a problem in galactic assembly, right? And so the approach to do this is to map 10 million to 100 million stars in this 9-dimensional space, which includes 3 dimensions of location, 3 dimensions of velocity, the metallicity or the chemical composition, the ages of the objects, and their types or subtypes. And this will inform our science. So how do we do this? Well, if we look at a galaxy, it has a very complex structure, right? It has a disk, which we divide into the thin disk and the thick disk. It has the bulge of the galaxy. This is a typical spiral like the Milky Way. It has a halo. And if we look at the environment surrounding our galaxy, we find that it has these satellite galaxies. So as of about 20 years ago, we knew of 3 satellite galaxies, right? We knew the Sagittarius dwarf and the small and large clouds of Magellan. If we look at galaxies, it's another light issue. Number 4. Yeah. So if we look at simulations, whoa, it's the same as 3, the bottom. So if we look at simulations of how galaxies form, so what's happening here, we have the prediction of the current cosmological model that we call lambda CDM cosmology, which stands for cold dark matter and dark energy existing in the universe. And what happens is that galaxies build up via collisions of smaller objects to form larger objects. And so what you see is that the environment surrounding the galaxy is there's a lot of action going on there, right? And so every galaxy is large galaxies like the Milky Way, not super large, but large enough, are predicted to have many satellite streams, right, of tidally disrupted structures and dwarf satellite galaxies. So for a galaxy the size of the Milky Way, we expect there to be something like 200 of these halo streams and dwarf galaxies. And the thing about the halo that's different as compared to the disk of the galaxy is that these structures should be long-lived. The gravitational interactions are sufficiently, they don't happen as often as they would occur in the disk. And so these structures should be long-lived, and we should be able to measure them today. Due to Sloan Digital Sky Survey data, we've identified something like 26 of these satellite streams and dwarf galaxies, which falls far short of the 200 that Lambda CDM measured. But if you look at what surveys have measured, they're only so-called pencil beam surveys, right? They cover very large, very small regions of the sky. These models also predict that the halo should have the chemistry should vary from the inner halo to the outer halo, right? You have a material that's been enriched with heavier metals, and then you have more recently accreted material, which should be of less metallicity. Also, if we map out all of these objects and all of their orbits, then it will tell us something about we will inform the galactic potential, right? Yeah, we can map the galactic potential based on this, and this could tell us something about the dark matter distribution in the galaxy. So this one isn't that important. So there's other problems that can be solved by this. For example, it was discovered that one of the foundations of astronomy, so in astronomy, my PhD advisor used to say to us all the time, the most important and the most difficult problem in astronomy is that of measuring distance. And the way that we measure distances is, the most reliable method is the method of parallax, which is simply geometric. But then after that, we use what are known as standard candles. These are objects of known brightness. And then by comparing the brightness of the object to its apparent brightness, we can tell how far away it is, right? And the cosmologists are thinking, yeah, there's a few more, but we're not going to talk about those. Now, what was discovered in the early 20th century is that there's a very large type of star, and it's important that it's large because we can see it to very far distances, that pulsates. And the rate at which it pulsates is related to how bright it is. And we call that the period luminosity relation. And so what was discovered is that this relation that we thought was, common to galaxies actually varies from galaxy to galaxy. So here we have the period luminosity relationship of the Large Magellanic Cloud, which is a satellite of the Milky Way. And we see that it's a broken power law. And it's different from the LMC to SMC and the galaxy. And so by discovering many different types of objects in different environments, like in different dwarf galaxies and different satellite streams that have very different histories, we can calibrate the Cepheids in those galaxies to calibrate this period luminosity relationship across the sky, right? Using the nearby universe. So here's a lot of science that may result from this Star-Vars project. We constrain in-body simulations of galaxy formation evolution and their environments. We can constrain the Lambda CDM models of universal evolution. We can map the galactic potential. We have a variability survey coming up called the LSST, and it has to design its cadences based on what actually exists out there in the universe. And so by looking at a large variability survey that precedes LSST, we can design LSST better, right, to deliver the science. So we can measure the variability baseline and measure the demographics of variability. There are certain regions of the variability parameter space that have never been explored. For example, high cadence, fast cadence, and very red. And so we just won a dark energy camera proposal to do that. We can calibrate the stellar distance ladder, as I mentioned earlier, with the Cepheids. And certainly we'll identify rare species, like these R-core Bohr stars. And then there's a lot of stellar physics that can be done that, nobody here is interested in. So, oh, you are? Oh, okay, cool. That's why we need to talk. So to do this, we require data sets covering large volumes of space, extending into the halo, and with time domain information. And we need to classify large numbers of stars, and we require machine learning classification and high performance computing to do this efficiently. So I'll talk about a couple of studies that I'm doing, and one is focused on what are known as RR Lyrae stars. So when you look at our galaxy in the halo, there are these objects known as globular clusters. And so these are about 1 million stars, right, in a very tight volume, and RR Lyrae stars are often seen in them. And here, for example, is an image, and you see these stars that are actually changing brightness, right? These are actually RR Lyrae stars that are pulsating and changing their brightnesses as they do so. Their size changes, their surface temperature changes, and so their brightness changes. And the thing about these stars is that they are standard candles. We can calibrate their brightnesses to about 5% error in distance. They're very bright, so we can see them very far. They're giant stars. And we can identify them easily based on the shapes of their light curves. And this is important. If we think back to the Eber-Curtis debate in astronomy in the early 20th century, there were this question of, is our galaxy the only one? We see these spiral nebulae, as they were called at the time, which we now know were external galaxies. And people were arguing, are they inside of our galaxy or are they not? And so the gentleman, Harlow Shapley, who had measured our the size of the Milky Way for the first time, he said, well, I've seen novae in these spiral nebulae, and I know how bright novae are. And so based on how bright they appear, I know that these spiral nebulae must be inside of our galaxy. And the young astronomer Curtis said, no, they're external. I don't know what his reasonings were. But what happened is that Shapley was not looking at novae. That's not what he was seeing. He was seeing supernovae, right, which are much brighter. And so these objects were much farther away. And so being able to distinguish one object from another is a very important piece of work that has to be done. So the first thing I did is an LSST simulation. So here's what I did. In Sloan's Stripe 82, which is only 300 square degrees, which is a small region of the sky, 483 RR Lyrae stars were observed. And these stars have a distribution of periods and amplitudes. And they come in two types, right? Here's one type and here's the other. RR Lyrae type A, AB, RR Lyrae type C. And so I took a distribution of stars that evenly sampled the period and amplitude period distribution. And here's what their light curves look like. Here are the 30 RRAB stars with very distinctive light curve shapes. And here's what they look like in the Sloan filters. And there were 10 RR type C stars. And this is my subsample out of the 483. And here's what their light curves look like. Excuse me. And they happen to look very similar to a type of eclipsing binary star called a W-UMA, these over-contact binaries. And here are the diversity of light curve shapes, and they vary primarily due to the differences in chemical composition. All right, and so I just show you this to show you that we, sampled the space of metallicities present in the data. And so what we did is we said, well, what is LSST going to be capable of doing? And we took these 40 stars and we placed them in 1,007 fields on the sky that represent different LSST observing cadences. So the blue dots are the so-called universal cadence. So every night the LSST will undergo the universal cadence. There are a total of 1,000 of these fields, and so we took a subsample of 400. Then these fields overlap so that you don't miss any location of the sky. You overlap them, and so these black dots are the so-called overlap regions. And on average, they're imaged twice as often as the universal cadence. And then we have the Milky Way fields, where we look at the galactic center. And then we have solar system fields, where we look at moving objects in the solar system, right? They're taken at higher air mass. And so we also looked at a range of magnitudes, right? Brightnesses of objects. So at the bright end of LSST and at the low end of LSST, the dim end. And so we have 40 stars, 1,007 fields, 15 different magnitudes, 6 different filters, and then we wanted to look at the evolution of information as a function of time. So after 1 year, what science can we do? After 2 years, so forth and so on. So we have 10 survey durations, and so we ended up with 36 million light curves, right? So now we have a problem in big data, right? We have a big data problem. So as a comparison, 36 million light curves, I was at the AIP in my role as a member of another organization. We're coming up with this idea that we call a virtual journal. And we were asking them, can we have access to your database? So it turns out that if you aggregated all of the physics journal papers ever written and all of the astronomy journal papers ever written into a database, which they have, they were talking about, oh man, it's huge. Nobody could analyze this data, right? It turns out that it was 30 million papers, right? So this is truly a big data problem. And so this is the workflow. Let me see something here. Yes, so this is a workflow for what you would generally do, right? So you observe an object over and over, you have your movie, and the first question you ask yourself, which objects are variable? Which objects are changing their brightness? And that is a much bigger, there's a lot more to that question than you may think, right? And that's something that we're actually working on, defining what does it mean to be variable. Like, for example, quite often when you look at the data, people perform what they call a 3 sigma cut, right? So I have an object and, you're going to have bad data. So how do I distinguish the bad data from the good data? Well, if the data is just an outlier, right, then let's cut it out. Well, what happens if the object did this? Right? You'd cut that out, right? So how do we approach this? The next thing, is the variability periodic? So there's period finding methods. I'll talk about that a little bit. And then you have to actually find the periods, which is a very inefficient process. For example, these 36 million light curves, we use the Athena computing cluster at University of Washington, which is a 1,000 node cluster, and it took months to calculate the periods for all these things. And then, what is the detailed shape of the folded light curve? We're doing things a bit different now, and I'll tell you how. So here's what our simulated data looked like. So the bright RR Lyrae stars, they don't have much photometric noise. Here we have more photometric noise. We have 6 bands. The cadences are not the same in all bands. And so we went about, and here's what the so-called deep drilling fields look like. Deep drilling fields, the way the universal cadence works, a given field is visited twice in a night. All right? A deep drilling field is visited 40 times in a night. There's 40 images. So this is what that data looks like. And so the first question is, can you recover the period, right? So will LSST be able to recover the period? Well, it turned out that no one had ever defined what it means to recover a period, right? So my collaborator, Andy Becker, and I, we talked to a lot of people that worked on other survey data. To what degree do we need to what precision must we recover the period to say we've successfully recovered the period, right? That was the question. And so I came up with this little equation here. And so the question is how much error can you stand? So you have data that looks like this, and you're going to turn it into this. How do you do that? You find the period, you divide the data by the period, and you're going to get a number like, so suppose from time 0, I subtract that time from the time of a particular observation, right? And if that time period is exactly 1 period, right, then you have 1.0. So you're at phase 0. If you find that the time minus the initial time divided by the period is some number 0.5, right? The fractional part is what you're interested in, so that's at phase 0.5, right? And so we call that process folding the data with the period, if you have the proper period. So suppose you're off a little bit. Suppose you fold it with the wrong period. Well, it depends on how many periods you're folding. Every time you, say for example, this is the proper period, but I think the period's that, right? So I'm off by that tiny amount. So I grab this data and make that one, and I do the same thing here. And what happens is that these little errors add up with the number of periods. And so you restrict those errors to some fraction of a full cycle, right? And then the number of periods is given by the total duration of the survey divided by the input period. The error in the period is given by this thing here. If I rearrange things, I found that if I have a period that's less than 10 to the minus 5 per day in error, then that will give me a successfully recovered period. So things with very short periods require a much tighter precision than things that, because they go through more cycles, than things with a longer period, right? So we use that defining criterion, and then we asked how well will LSST be able to recover periods. So how do we define recovering a period? Okay, so the second part of this is I have 6 different photometric bands, 6 colors in which I'm taking data. And what astronomers have generally done is they take one color and you search for a period in that data. All right, so you don't have to think hard to realize that the more data you have, the easier it is to find the period, right? And so if I do it one color at a time for the universal cadence, there's no way I'm going to get a period from this data. right? And so if I use one band at a time, that's going to be a very inefficient process. So somehow, can I think of a way to combine all the bands in order to recover periods? So here's what we have, and the end result of this is that, you know, LST is going to be able to find all RR Lyrae, recover their periods out to something like 600 kiloparsecs in the universal cadence, and in the deep drilling cadence, it's going to be out to about a megaparsec, out to say the Andromeda Galaxy, right? No one expected that. The guess before we did this study was about 300 kiloparsecs. So the next thing we want to do is we want to recover the shape of the light curve, because remember, the shape of the light curve is related to its chemical composition. So we perform a Fourier decomposition of the magnitudes as a function of time, right? And then there's this relation of the metallicity. So every harmonic in this Fourier series is going to have an amplitude, which for some reason doesn't appear, and a phase. And so if we look at the difference in the third and first harmonic using this sort of thing, the phase of third and first harmonic, we get this thing called delta phi31. Excuse me, phi31. And so the metallicity is related to the difference in these harmonics, and it's also related to the phase to something like the error is about I don't remember, so I'm not going to say it. But here's a relation here, right? Here's metallicity, here's phi31. And so what we did is we took different amounts of data, 1 year of data, 2 years of data, 5 years of data, 10 years of data at different brightnesses, and we compared how our ability to measure the metallicity fell off with distance and time, right? Or improved with time and fell off with distance. So what we plot here is delta phi31, which is the difference between our input phi31 and our output phi31. That makes it independent of any particular metallicity relation. And we looked at how well we'd be able to recover light curve shapes, and we do pretty well, right? But what we see here is after 1 year of data, we don't really do so well. And this is only for stars that have actually had their period successfully recovered, right? After 5 years of data, we do much better, but then 2 years, excuse me, but then at 5 years, we pretty much reach our limit there, right? Here's the universal cadence over here. So after 2 years, you get nothing out of the universal cadence data for the most part. So here's what we discovered, right? So the single color approach to finding magnitudes isn't good. Can we somehow combine data from multiple bands? And so if we can do that, one of the things that's been very important in recovering periods is this is the result of what we call a template fit period recovery. So what do I mean by that? If I take my input light curves, which are templates, and I perform a Fourier decomposition of them, I'm sorry, I think my phone is ringing. Let's ignore it. And I perform a Fourier decomposition of the light curve data itself using this formula right here. I can recover, maybe it sounds like it's coming from back there. I can recover over there. I can recover the metallicity, the shape, with a particular capability, right? But if I first fit a template to my data and then form a decomposition of the best fit template, I recover to these high fractions that I see in here, right? And so this whole notion of having templates is incredibly important. And so if we extend our period finding to 2 dimensions in phase and color, then we should also be able to define these 2-dimensional, instead of light curves, light surfaces, right? And then we can get higher metallicity relations. So we did that, all right? So working with an actual statistician, Joseph Richards, what we did is we found a way to fit the surfaces with what is known as a thin plate spline, right? So let me tell you how this works. So we take all the data. Well, let's talk about finding periods in a single band first. There's different ways of doing it. And what happens is that, let's take the most naive method. Let me try to fit all periods to the data. I have this data. I'm going to divide it by every period possible. What happens that's magical when I get the right period? What happens is that the data has the least amount of variance, right? It kind of zeroes in. It becomes very sharp. And so one of the main techniques for finding periods is what's called super smoother. It was a guy's PhD thesis in the 90s at Berkeley, a math student, and super smoother looks at the light curve in segments, and it selects the period that has the least dispersion in each segment. All right, and so these are generally called phase dispersion methods. And so what we said is that instead of requiring smoothness only in phase, let's also require smoothness in color, right? And so we get out a period, and so we take slices at the filters that correspond to Sloan wavelengths. You see that the data fit the fitted 2D surface very well. Does that make sense? The black dots here are the data. The blue dashed lines are the slices across the template, and they fit very well. So what is this thin plate spline? So typically we do something like this. We minimize a chi-square that compares our predicted magnitude to our actual magnitude divided by the error. And so our requirement of smoothness in color comes from this second term here, right? So we have a second derivative in both phase and color. And the second derivative is it's bigger when the thing isn't as smooth, okay? And so we have the scaling parameter here, gamma, as well. So this is a penalization parameter that you're penalized for not being smooth. So by requiring smoothness, you minimize this sum. And then we calculate what's known as a GCV score. And what you do is that you take your model and you remove each data point, and you have your model predict what that data point's value would be, and you compare that difference, right? And that's how you get your GCV score. And here's how this thing is performed. So here's the criterion that we set. So down here, we have the true period compared to super smoother 1D, right? The 1D method. And here we have the true period compared to super smoother 2D. So in the 1D method, for the sample of light curves that we use, which is 42 plus 24 plus 30, what's that? 72 plus 24 is 96. For these 96 light curves, under this line are all the ones that were able to have matching periods or successfully have their periods recovered using 1D data. Using the 2D techniques, we get 66, right? So now we're in the process of doing this for our full LSST simulation. And so what this shows is that, right, so here, these errors, these will not, these don't have their periods recovered successfully. 1D, you have 42. 2D, you have 66. So that's going to revolutionize what LSST can do. Because if you look at these curves, these period recovery, after 1 and 2 years, you don't recover any periods. So when we recalculate these curves, which we're in the process of doing right now, I'm assuming that these 1 year and 2 year curves are going to move up here, right? So that's going to substantially change how LSST is going about its business, we think. So the other thing is that how do we come up with these templates? So we're using standard methods that all statisticians know, and we're using machine learning techniques, and so I'm using hierarchical clustering. So if I take a light curve, right, and I say my light curve, I fit a spline to it, so each light curve is 100 data points, right, between 0 and 1, all right? So that light curve then is going to be represented as, say my light curve was 3 numbers, right? I had 3 data points, right? So that's like a vector, right, in 3D space. But instead I have 100 data points, so that's like a vector in 100D points. So for light curves that are similar, if I want to make templates, then they will not be very far from each other in this 100-dimensional space. So all I have to do is do distance-based clustering analyses to define my templates. So here is, for example, in the G band, the R band, these are dendrograms that, I just showed them because they're pretty, right? Did anybody learn anything from these? Yeah, me either, but they're pretty, right? So that's part of the science, right? You look at them like, oh, that's complex. That dude must be smart. So students. And here is for the RRAB separate from the RRCs, right? There's only 100 of these. But what you see is the distance in the vertical is the distance apart these guys are in this multi-dimensional space. So there's different ways of defining either a similarity matrix or a distance matrix. And that's one of the things that we're exploring, how to do this optimally. And so here are the very, very, very preliminary results. Some of the clusters that we found. So here's cluster 1. So this is phase, this is wavelength. And what you see is that the red here is the phase of minimum light. And so you see that what defines it is pretty much that. So you see these surfaces look similar for these clusters for RRAB stars. If we look at these for RRC stars, right, they're similar-ish as well. So, so we're just defining these templates. And so the other project that I'm working on is the linear survey data. So the linear survey is a survey that covered about 25% of the sky, and it repeatedly observed the same regions of the sky. So if you look at all the all-sky surveys that exist, most of these surveys visit the same region of sky like 20, 30 times, right? So if you look at the numbers here, the average value is about 200, and then the plane of the solar system is about 400. So the linear survey is two telescopes that are just bigger than 1 meter, and their purpose is to find objects that may impact Earth, right? Near Earth objects. And it's a military survey, right? It's done by the Air Force. So astronomers have not been given access to the data. But my collaborator, no one has seen the images outside of the team. My collaborator, Jelko Ivezic, somehow got access to the data. He said, we can calibrate this data for you against the Sloan Sky Survey. So his graduate student at the time, Branimir Cesar, did the work. And then I joined those guys, right? Because that's who I did the LSST work with. And so here are example light curves from linear. Linear is different from the other surveys in that it's a bit deeper, right? It's magnitudes 14 to 18. Most of the other ones extend to about magnitude 13. So here are the quality of the light curves. So here's an RRAB, here are a couple eclipsing binaries, and here's what they look like as you get out to magnitude 17. This is near magnitude 15. And so we are now at this very moment in the process of classifying these data. And so what I'm doing next week, I'm going to my colleagues in Berkeley. We're using the supercomputer at NERSC, which stands for National Energy Research Computing Center. And I'm going to train the software to look at the linear data. And this slide simply shows that if you find in one survey, here's the Hipparcos survey, that, these RR Lyrae and these classical Cepheids and these mirror stars are separated, right? This is like looking at a clustering, yeah? Very well in this period amplitude space. If I apply the same criteria to the Ogle survey for the exact same types of stars, it doesn't work, right? So you have to train your software on each data set individually. And then your training data will consist of examples. These are different types of stars. And so if we look at their periods in this space, they all have some distribution. And so if we look at their amplitudes, they have a distribution. And so you can look at this as a decision tree technique and classify these things very efficiently. And, here's how the classification works. And that's what we're doing. Thank you. So, questions? Yes, sir. Yes. Really? Not from what I can tell. The algorithms themselves. Yeah, we just use algorithms that exist. So SciPy and Python, I use SciPy methods. So there's SciPy.cluster methods, and there is so-called scikits, also now called sklearn, right, which is machine learning. And they're not as efficient. And the statistical package R, you know R, that coding language. And so I use RPy, I use R from Python. We just use standard R methods, and it's much more efficient. So my collaborators at Berkeley, so I did a lot of the linear stuff with those guys last summer, and a month after I left, they started a startup company that provides machine learning for money, right? And so they're just using standard R methods to do that, and they give you the efficiency of R versus the scikits versus what people do who are not, nerds like us, right? The biologists, like biologists are way ahead of us. The people that do genetics, they're way ahead of astronomy in this kind of science, right? And so, in this kind of science, I'm sort of a pioneer, right? All these surveys that have done this in the past, like ACES use an algorithm that, the Bloom guys use theirs, and they found like many more classes and And the difference is that when you ask astronomers to do it, we know what we know, right? And so what Josh had the brilliance to do was to hire an actual statistician to do it. And so it's sort of like going into being one of the first people in Antarctica. You're like, oh wow, there are meteorites just sitting on the ground everywhere, right? So, and it's the exact same way. I went into Silicon Valley out of doing graduate work in astrophysics, and I took spectroscopic techniques I learned in astrophysics and applied them to making computer chips, and it resulted in 5 patents and a whole new division of the company, right? Because, it was just stuff that I just happened to know because I'm in a different field, right? And so that's kind of where this is. So a lot of it has been built for us. We just don't know how to take advantage of it, and that's what I'm trying to do now. Yes? Well, no. So the linear survey has 5 billion photometric measurements for 24 billion objects, and it's on the hundreds of gigabytes size scale. Yeah. Now, the LSST, I thought now. Yeah, 10 terabytes a night. But my understanding, working directly with the team on the project that's doing that, was that we are keeping everything. It's not like Kepler that throws it away, or like the particle physicists that.
What I meant was, I can't download it.
Oh yeah, you definitely can't download it. Yeah. And when I say you can't download it, I don't mean like people in general. I mean you specifically. No, just teasing. No, you're absolutely right, and that's one of the big problems, and that's why I'm partnering, right? So one of the things that my colleagues do, so after doing this stuff, the guys at Vanderbilt will say, hey, work with us, right? So they have their own survey data Kelt. We're just getting started. And the difference between these guys is that they can download an entire database locally, right? Because one of the things we have to do for training the data set is we need a set of objects that we know what they are. And you do that via database cross-matching, right? So I have the coordinates of these guys in linear, and so now I'm going to take the Sloan data, because they do overlap in 10,000 square degrees, and we're going to, cross-match these databases to get labels on all these guys. So then when we do our analyses, right, which is just standard machine learning stuff, it can be successful. And, me being a small guy in a small school, and I don't have a large computing problem, I can't do this. So it turns out that I just got on this committee for Sloan Digital Sky Survey that's addressing exactly this problem, right? How do we bring in other people who are not, amazing giant schools that are super rich and have incredible scientists like Texas A&M, right? How do we, how do we help these people? And so I was on that committee, and I was like, yo, man, we need computation. And guess what? It's now happening. Yes, sir. That was someone, yeah. Well, no, this one was stored at MIT Lincoln Labs, and there are these military experiments that exist, right? And you actually have to be on site to access that data. That data can't go anywhere. This data was released in a very different way, right? It's not like you got images, right? You actually had, here are locations on the sky of objects that we're going to release. And here's the brightness measurement, here's the time, and here's the error on the brightness measurement, right? And so it was originally given in their own magnitude system, and they had to be cross-calibrated against calibrated Sloan data, right, in order for it to be useful scientifically for astronomers. Excuse me. So that's not, for linear, that's not necessarily the case. And, people are tight with their data. So, for example, you wonder how certain things happen. Oh, we're going to release our survey to the world for free. And then 2 months later, oh, here's a big paper on this data, right? They obviously had access to the data prior to the release, right? So here's the thing that's happening in astronomy now. Proprietary data has always been a big thing. And we're moving away from proprietary data. But now the problem is proprietary knowledge, right? If I give you the Sloan Sky Survey data for free, do you know what to do with it? Not many people do, right? And so, some of the work I did was in solar physics. And literally, if you look at this one experiment called SUMER, it was a spectrograph, you notice that only members of the SUMER team published SUMER papers for a long time. They gave you software, here's how you reduce and calibrate the data, but it didn't work, right? So so people play these games. So yes, sir.
I wanted to comment that LST will provide pipeline calibrated data.
Exactly.
So national data sets
Yeah.
You'll be able to
Do what you envision.
come up with your smart query to find red galaxies. You'll be the first one to run the query to write the code table.
But chances are,
You don't need a 10 petabyte on your system.
Yeah.
You need to switch it to the next layer.
yeah, and if you are if you are interested in a particular object, it probably would not be difficult for you to download all those particular types of objects, right? It's not going to be the full data set. So if you're interested, Yes, sir.
I was wondering why you were talking about looking for these periods.
Yeah.
When you find the period, how do you know that that's one process that has this one period?
Exactly. Exactly. And so we're doing exactly that. So our technique for doing that, like one of the things we're looking at is pulsators in eclipsing binary systems, right? So we basically fit a curve to the main light curve, right? That's fitted at that period, subtract that off, and then period search the data, right? And then rephase it and see what we find. Yeah. And by the way, I just want to say all this stuff is new to me, man. I just started this in like 2009. So all the astronomers in the room, I apologize if I ruined anything. If I misled your students. Yes. Any other left-hand side of the room questions? Not you. I know your questions. They're going to be something I can't answer.
All right, let's thank our speaker again.
Thank you.